Okay, we're in part two of chapter 19 on vibrations and oscillations. And I'm going to start with another Walter Fenton demo, but instead of a swinging pendulum, now we're going to use a, uh, a spring pendulum. Uh, and I think it's a little more logical to see it this way than uh, with a swinging pendulum. And so let's just start this, and you can see that you can very easily see how the up and down motion of the spring pendulum mimics and gives us a sine wave. And what we want to do, let me pause this. Actually, let's try to uh, pause it right at the top. The way we measure uh, waves, there's wavelength, and there's frequency, there's period. The way we measure wavelength is from peak to peak. That's one way. You can from peak to peak. The opposite would be from trough to trough. But there's also a way to do it where you look at the zero crossings when it crosses the zero. But you have to be careful because if you are measuring at a downward going zero crossing, you have to measure from the others downward going zero crossing. If you just go from this zero crossing to this one, you've only measured half of a wavelength. That's not a full wavelength. You can see it has to be going in the same direction. But you can see how a spring pendulum, if we resume, it makes a sine wave, and those are some of the parameters. The wavelength, the period. The period here is 3.14 seconds. Now uh, the spring pendulums are their their period is based on this is based on the mass, and it's also based on the spring constant. But we won't get into that right now. This was just to show you um, how a oscillating spring pendulum mimics a sine wave. So let's do a new share with the PowerPoint. So we ended part one, and now we're at part two. I'm going to dismiss my image. Oops, I went too far. And you can see this is uh, Oppenheimer, the brother of the famous Oppenheimer that they just put the movie to, and he's actually got a pendulum that drops sand, and as this paper moves, you can see that it makes a sine wave. So a wave is pictorially represented by a sine wave. A sine curve is obtained when you trace out the path of a vibrating pendulum over time, or it could be a spring pendulum, as we just showed you with the Walter Fenton demonstration. Put some sand in the pendulum and let it swing. The sand drops through a hole in the pendulum onto a sheet of paper. As the pendulum swings back and forth, pull the sheet of paper on which the sand falls. The sand makes a sine curve on the paper. Um, the uh, so that's what they're demonstrating here, and they have here they have a swinging bob. This is a spring pendulum. This isn't um, the this isn't a regular pendulum. When a bob vibrates up and down, a marking pen traces out a sine curve on the paper that moves horizontally at constant speed. And what are the things that we look here? You can see from peak to peak, that's a wavelength. From trough to trough, that's a wavelength. Notice here they have an arbitrary point where they're measuring wavelength, but notice that it's always in this particular case, it's on the upgoing trace. It goes up, and that's a wavelength. You can't just go from here to the same point here. That's insufficient. Um, or you can't go from the zero crossing to the next zero crossing. You have to go on the upgoing zero crossing to the next upgoing zero crossing to get the wave. And let's so vibration and wave characteristics. The crests are the high points of the wave, and the troughs are the low points of waves. So these are the crests, These two are the crests, and these two are the troughs, and they don't say it here, but there's zero crossings, and you'll have 2 0 crossings between every crest and every trough. Okay, vibrations and wave characteristics continue. The amplitude, the distance from the midpoint to the peak or the crest, from the midpoint to the crest, this is the midpoint here of the wave, to the crest or to the trough is the amplitude. So this is the amplitude and this is the amplitude. It's how much it deviates from the center. The wavelength is the distance from the top of one crest to the top of the next crest, or the distance between successive identical parts of the wave. Now, the identical is very important in that the direction you're going has to be in the same direction. If you're going up, it's to the next upgoing part of the wave at the same position. Okay, frequency. Now, frequency specifies the number of to and fro vibrations in a given time. Typically cycles per second. And we have a name for that. Cycles per second is given the name Hertz, Hertz. Now, the number of waves passing any point per second, cycles per second. Example, 2 vibrations occurring in 1 second is the frequency of 2 vibrations per second. If you have 4 vibrations occurring in 1 second, it's 4 vibrations per second, or 4 hertz, or 4 cycles per second. Okay, so the period is the inverse of the frequency, the time to complete 1 vibration. The period is equal to the inverse of the frequency, and the frequency is the inverse of the period. As an example, a pendulum makes 2 vibrations in 1 second. The frequency is 2 hertz. The period of vibration is 1/2 second, since it's the inverse. Okay, a sound wave has a frequency of 500 hertz. What is the period of the vibration of the air molecules due to the sound wave? Well, 1/500 would be 0.002, which is 2.002 seconds. So the answer is C. So 1/500 hertz is 0.002 seconds. Okay, the frequency of a particular wave is 20 hertz. So its period is the inverse, the reciprocal, which is 1/20th of a second. Okay, there we go. The period is equal to 1 over the frequency is equal to 1/20 hertz, which is 1/20th of a second. Okay, you could say if hertz is cycles per second, well, this is 1 over cycles per second, so it ends up seconds per cycle. So it's 1/20th of a second per cycle. That's another way to think about it. Okay, wave motion. Waves transport energy and not matter. If you drop a stone in a quiet pond and the resulting ripples carry no water across the pond, all they're going to do is the same water molecules are just going to bounce up and down. The water itself doesn't go out, just the waves propagate, and the waves are just the water going up and down. You could, if you were to have some kind of little float, and you could, drop a pebble in a undisturbed pond, you would see that the float, the little bob, would just bounce up and down. It wouldn't travel away from where you dropped the little pebble. Waves travel across grass on a windy day. They don't. You see this field of grain, and you see the waves. The grain isn't moving, but you can see the wave moving the grains of wheat or grass or whatever it is. Molecules in air propagate a disturbance through air. So as I speak, the molecules are carrying the information to the microphone as I speak. It's the compression and rarefaction of the air molecules that creates the sound. Okay, now the wave speed describes how fast a disturbance moves through a medium, related to frequency and wavelength of a wave. So the wave speed, the velocity, the wave speed is equal to the frequency times the wavelength. Frequency is F, wavelength is the Greek letter lambda. So the velocity is equal to F times lambda. A wave with wavelength 1 meter and a frequency of 1 hertz has a speed of 1 meter per second. Now, the speed is related to the medium that is that the vibrations are traveling through. Now you could, if you like had a drop of water dropping once per second, you would get a 1 hertz wave. If you dropped it two drops per second, you would have a 2 hertz wave. But the wave motion is related to the speed of the wave in the water. The speed of like the speed of sound in water is a given amount. And I don't know what it is. It's faster than the speed of sound in air. The speed of sound in air is about 340 meters per second. In metal, it's very fast. It's on depending on the metal, it's thousands of feet per second. So it depends on the medium, the speed of the wave. Okay, a wave with a wavelength of 10 meters and a time between crests of 0.5 seconds is traveling in the water. What is the wave speed? Well, it would be 10 meters divided by 0.5 seconds. So that's really 10 meters divided by 1/2 of a second. So you take the reciprocal of the 1/2 and it ends up being 2 times 10. It's 20 meters per second, D. There it is. So the frequency is 1/0.5 seconds, so that's 2 hertz. So the wave speed is equal to the frequency times the wavelength, so it's 2 hertz times 10 meters is 20 meters per second. Oh, and that's the end of part 2. We'll end it here.